more on internal resistance. If we consider the internal resistance of a cell, we can use the cell and the resistor symbols together like this. Boom. And we may enclose the whole circuit as a box of some sort to show that it is one unit. So we have that loop. Suppose we connect our cell with internal resistance, lowercase r, to an external circuit consisting of a single resistor, capital R. All of the chemical energy from the battery is being consumed by the internal resistance and the external load represented by capital R. So we have our electromotive force here happening within the cell, and then we have the internal resistance, lowercase r, and then we have capital R, the resistor resistance for the circuit. So this is all happening inside of the cell. The internal resistance, the electromotive force, and then one resistor on this circuit. So there we go. From work equals QV, we can deduce the electrical energy being created by the cell equals the electric potential Q times E. The electric energy being converted to heat energy by R is E equals Q times V R. The electric energy being converted by heat energy is E equals QV R. And from conservation of energy, the electric potential energy equals electric potential energy of the resistor plus the electric potential energy of the cell. So QE equals QVR plus QV little r. Note the current is the same everywhere. From Ohm's law, V equals IR and V equals IR. So epsilon equals I times big R plus I times little r. All of that stuff right there, you can go back and get it in your head. I know I blew through it really fast. That's because it's just going through the entire derivation for the formula for electromotive force, which is, here we go, epsilon equals IR plus I little r. So your data booklet's not going to have all of this. It's going to be I times big R plus little r. This is the EMF relationship. So you can calculate your EMF by using your internal resistance, the resistance of the circuit, and the current of the circuit, because the current should be the same everywhere. Looking at an example, a cell has an unloaded voltage of 1.6 volts and a loaded voltage of 1.5 volts when a 330 ohm resistor is connected, as shown. Boom. Find the electromotive force for part A. So, to find the electromotive force that's given to us, the unloaded voltage is 1.6 volts. It's just going to be 1.6 volts for the electromotive force because it's unloaded. For part B, find the current. From the second diagram, we see the voltage across the 330 ohms is 1.5 volts because it's a loaded cell. And we know that V equals IR. So 1.5 equals I times 330. So I must equal 0.045. For C, find the cell's internal resistance. We have the electromotive force of 1.6 volts. We have the current. We have the resistor. So all we're looking for is little r in that equation, which is epsilon equals IR plus I little r. We know I is going to be the same, so we get 22 ohms. Go back, try that problem for yourself. Pretty easy, straightforward, as long as you understand your definitions. For part D, what is the terminal potential difference of the cell? Terminal potential difference is the potential difference at the terminals of the cell where it connects to the external circuit. The cell has an unloaded terminal potential difference of 1.6 volts and a loaded terminal potential difference of 1.5 volts. Note that the terminal potential difference depends on your load. You add more stuff to your circuit, your terminal potential difference is going to decrease. Those are the terminals. That's it. That's all I've got for you for 5.3. Very small section. Make sure you do lots of practice problems. Obviously, have your definitions down. Electric potential difference, potential difference, terminal potential difference, electromotive force. All roughly the same kind of thing, but each has its own particular definition. So definition, and work through circuits until you can get through them extremely quickly.